Hello and welcome to Lecture 2 of Robotics, Kinematics, Dynamics and Applications, where we'll be talking about motors and servos. Okay, so in today's lecture we'll be talking about DC motor configurations, we'll talk about driving DC motors, we'll talk about a common technique known as pulse width modulation, which some of you may have come across before from your undergraduate studies. We'll then talk about the H-bridge configuration or the Wheatstone bridge configuration. We'll do some work on stepper motors and then finish off with servo motors. Okay, so the most commonly used methods for locomotion in mobile robots are DC motors. This is because they're clean, they're quiet, and they can produce significant power for a variety of tasks. For example, you can move a little small mobile robot around, up to robotic wheelchairs, up to the big ABB robot arms that are used in automated manufacturing plants. They're much easier to control than pneumatic actuators, which are mainly used for very high torque applications, but these require umbilical cords and require external pressure pumps in order to provide the compressed air to run them. Standard DC motors revolve freely, unlike stepper motors or servos, for example, but need to be a bit more control behind them. We'll talk about these in the lecture later on. Okay, but for the moment we're just going to focus on DC motors. Okay, the motor control requires some form of feedback mechanism, such as a shaft encoder, that we'll cover in lecture number 3. The best choice when building a robot is to use an encapsulated motor combination unit, which already has the motor, the gearbox, and the optical and magnetic encoder to measure the revolutions of the shaft. Okay. The advantage of that is it's much better than using separate modules, as they're shielded against stray light, dustproof, waterproof, so on and so forth. So it's much better to get a already built purpose module. Obviously, things like final year projects and MSc level projects would get you building your own shaft encoder or gearbox for such a system. So that gives you an idea of some of the techniques, and some of those projects will be available to you when you come to doing your M04AEE module. Okay, this is just some revision about the different types of motors. So obviously this is a series excited motor. So here you've got the rotor, here you've got the stator, here you've got your coils, there's your brushes there's the commutator, there's stator coils, etc. So if you connect them in series, you connect the coils here to the rotor and back, so everything is in series. So the windings are in series with the load, magnetization increases as the load draws current, and the output drops significantly as the output draws more current. Some of this will be basic revision that you have done at undergraduate level, but it's good to go through this stuff so that everyone's working from the same level. There's also some basic level 1 undergraduate notes on electrical engineering available on the course web, which has some extra information about this from undergraduate level. So if you want to learn a bit more about this, if you've not done this before, then you can have a look at those notes there. Okay, this is the self-excited shunt configuration. So as you can see here, the field windings here are in parallel with the load and in parallel with the shaft. So as the load increases, the output voltage will drop due to the armature winding resistance, and therefore as the load increases, the field winding current reduces. And we'll be going over some graphs and configurations later in the lecture. This is a compound which has a split between series and parallel. So half of it is in series, half of it is in parallel. And this is the configuration that it would be in. Okay, so this provides an increase in load current, which boosts the winding current, and the generator self-compensates the voltage drop as the load increases across here. Now the last configuration is you've got big, heavy permanent magnets located here, which go there, and you've got the voltage across there. So they're simple, but the downside is that the magnets are quite heavy. So obviously you need to compensate for that when you're doing your weight to torque ratios of your actual mobile robot. Okay, So this is a comparison of the different field generation techniques. Okay, so series motor, there's a motor, there's the windings in series with it, there's the shunt with it in parallel, there's the compound motor with the windings in series and parallel, and then there's the permanent magnet motor like so. Okay, so here on the right hand side of these are a number of different graphs. So the x-axis is torque and the y-axis is either speed or current. So for a series motor, as the speed decreases as the torque increases in this decaying exponential curve, whilst the current slowly increases. For a shunt motor, it's this configuration here. So speed stays fairly constant until a certain point when it starts to decrease quite rapidly, and the current follows a similar trend as it did for the series motor. Again, for the compound motor, the current follows a very similar format, except this time the speed doesn't drop as much with the torque, and for the permanent magnet motor, then it's pretty much a linear characteristic. So the current increases linear with torque, and the speed decreases linearly as torque increases. The next thing we're going to look at in some more detail is the DC motor model. Okay. Now, due to the variety of motors and gearbox combination available, it's important to do some power requirement calculations when you first initially start to design your system. So you need to select the right motor and gearbox for the desired application. Okay, motor manufacturers such as Faulhaber range from having 2 watts to 4 watts with a gear ratio of anything from 3:1 to 1,000,000 to 1. So you need to be aware of this when you're designing your system. Okay, so let's talk about the basic DC motor model. Okay, and it's shown here in this image. Okay, so you've got a variety of different variables which are shown on the next slide, but I'm going to talk you through a lot of them now while I've got this figure up here, and you can look forward in your lecture notes which are available on Moodle to see what each one of the terms means. So obviously I'd have a theta, which would be an angular position of this shaft. Obviously, if I have a theta, I've got an omega, which is angular shaft velocity, which would be in radians per second, and an alpha term, which would be the angular shaft acceleration in radians per second squared. Because obviously, remember, if you differentiate from position, you get velocity, and if you differentiate velocity again, you get acceleration. Okay, you would obviously have a current, which would go through the armature, demonstrated where my laser pointer is now. You'd obviously have an applied terminal voltage, which would be across here. Excuse me. You'd obviously have this back EMF here measured in volts. You'd have the motor torque, which would be the T tau motor, which would be this here. You'd obviously have an applied torque, which would be the load which is actually applied, and those two will be measured in Newton meters. You've obviously got your resistance here, which is your nominal terminal resistance in ohms. You've got your rotor inductance here measured in henries. Here you've got your rotor inertia measured by J, and that in kilograms per meter squared. You've got Kf, which is the frictional constant, which is down here, and you've got the torque constant Km measured in Newton meters per amp. The back EMF constant Ke measured in volts per second per radians. Ks, which is a speed constant in radians per volts per second, and the regulation constant. So basically, this whole figure excuse me, illustrates an effective linear model for a DC motor. This will be the only model that we cover in this module, because obviously the people doing the MSc in Electrical Engineering and Electronics, they do a whole module in electrical machines and drives. So I don't want to step onto that module leader's toes too much. So this is the most I'm going to go into it in the terms of motor model. Okay, and you can read up more about this in a book called Embedded Robotics: Mobile Robot Design and Applications with Embedded Systems by Springer, and it's written by Thomas Braun. Okay, and like I said, all the list of parameters that I've just mentioned are on the next page. So when you have a voltage VA applied to these terminals here of the motor, this generates a current I in the motor armature as such. Okay, then you have this torque tau m produced by the motor, which is proportional to the current. Okay, and that's Km. So that's what the Km term was, the motor torque constant. Okay. It's important when you do this to select the motor with the right output power for a desired task. The output power P out is defined as the rate of work, which for a rotation DC motor equates to the angular velocity of the shaft, omega. So basically how quick this shaft spins multiplied by the applied torque, tau applied here. So P out is equal to tau A omega. Okay, so now I'm just going to skip ahead a few slides to show you where these equations actually come from. So this shows you all the variables that I've just mentioned. I mentioned those talking through the previous slide, so I'm not going to go through those again here. So like I said, here's where we're developing our model. So we've already mentioned that we get this, the torque tau m produced by the motor proportional to the current, and Km is the motor's torque, which gives us this here. So we have tau m is equal to Kmi. So as we said, it's important to select the motor with the right output power for a desired task. The power out is defined as the rate of work, which for a rotational motor equates to the angular velocity of the shaft omega multiplied by the applied torque A. So P out is equal to tau A omega. Okay, and the input power supply of the motor is equal to the applied voltage multiplied by the current going through it. So you got Pi is equal to VA times I. However, as we've all know when we've played around with motors before, the motor also generates heat as an effect of the current flowing through the armature. That's why we've got that armature resistance inverse, or the nominal terminal resistance that I mentioned earlier. So the power loss to the thermal effects PT, or P power thermal, is equal to I squared R. Okay, so it goes back to our basic undergraduate basic electrical engineering concept. The efficiency N of the motor is a measure of how well the electrical energy is converted into the mechanical energy, and that's defined obviously as we know from the output power produced by the motor divided by the input power. So we can say that the efficiency is equal to P out over P in, which equals, when you go through all the previous equations, is equal to the applied torque tau A times omega divided by the applied voltage times the current. So tau A omega over the I, over VAI. Okay. The important thing to know is that efficiency is not constant for all speeds, and the electrical system of a motor can be modeled by resistor inductor pairs in series with the voltage source. Look back at slide 11 for where it fits in, and that corresponds to that back electromotive force. So this voltage is produced because the cores of a motor are moving through a rotating magnetic field, which is the same principle in an electric generator. Okay, those of you who haven't done generators before, if you've come from a more electronic background, there's some information on the course web that can help you there, but I'm not going to repeat that content here. Okay, this voltage produced can be approximated to a linear function of the shaft velocity Ke, and so we can relate that back velocity to the shaft velocity by Ve is equal to Ke times omega. Okay. Again, here's some more equations. So the motor inductance and the motor friction are negligible. So what we can do is we can set those to 0. Motor inertia is represented by J. So therefore we can approximate our current and angular accelerations as such. So I is equal to minus Ke over R times omega plus 1 over R VA, and delta omega delta T is equal to Km over J times I minus tau A over J. Okay. Okay, this carries the model on a bit further. So this shows you the ideal DC motor performance curves. So with an increase in torque, the motor velocity is reduced linearly, which is what's shown here, like so, whilst the current increases linearly. So it's similar to the graphs that we were shown before. And then the maximum output is achieved at a medium torque, such as here. So the graph increases like that, whilst the highest efficiency is reached at a relatively lower torque, so namely here. It's like when you're driving your car, the most efficient speed you can drive at is about 55 miles an hour. So if you're driving in a city at 30, it's not going to be that efficient. Then again, if you're driving on the motorway at 70, it's not going to be that efficient either. So dual carriageways are pretty much the best speed you can drive at. So it's the same thing here. You can think of it as an analogy to different motors. So you can have a further read about that. Okay, so now we've looked at a typical motor model. Now let's look at driving DC motors. So usually a voltage is available from a controlling device, and that needs to be translated into power capable of delivering the power to the motor. So servo amplifiers are commercially available to perform such tasks, and when driving is carried out in an analog fashion, a push-pull output stage is often used to enable motions in both the forward and reverse directions. Okay, and here's the circuit for a push-pull system. So here you've got your pre-amplification stage, which feeds into your transistors, which would then power the motor there. There's more literature in the textbooks and online, so as this is a general common circuit that is used at undergrad level, I'm not going to discuss it in that much detail here. When driving a motor, however, with a constant voltage, the back EMF ensures that the current will eventually reduce to a point where the accelerating torque is just about enough to overcome the friction, so you get a maximum speed reachable. And many control operations however require control over the torque, so it's possible to add a current sensing resistor to make this possible, and that's explained on slide number 22. So the control is now proportional to the current rather than an amplification of the output current. So that's when you add your current sensing feedback system into it. However, the most common method we use is pulse width modulation, okay, or PWM for short. And this is a smart method for avoiding analog power circuitry by utilizing the fact that mechanical systems have a certain latency in them. Okay, so instead of generating an analog output signal with a voltage proportional to a designed motor speed, you can actually generate a series of digital pulses, okay, at the full system level voltage, for example, something like 5 volts, and these are then generated at a fixed frequency, so 20 kilohertz, for example, so they're beyond the human hearing range. Then by varying the pulses, like the graph that's shown on the next page, we can also change the equivalent or effective analog motor speed and therefore control the motor speed itself. So one could say the motor behaves like an integrator of the digital input pulses over a certain time span. And the quotient or duty cycle, which is this T on to T off, is called the pulse width ratio or the duty cycle. Okay, so here's an example. So here we have relatively small pulses, as you can see, with large gaps in between them. And this is equivalent to like a low voltage output, which will give you a low speed. Here you've got much wider pulses, so with a smaller gap in between, so this is equivalent to a higher speed signal, okay, or high voltage. So pulse-width modulation can be generated by software, such as with the PIC18F microcontroller or other microcontrollers, such as the M68332. The PIC18F has two onboard PWM generators, and you can multiplex those to get more, and you can also modify the timing signals to do other things. Things that microcontrollers like the M68332 have special modes and output ports for support PWM operations as well. The digital output port of the PWM signal can then be connected to the speed pin of a power amplifier, such as the ones that we've shown previously. Okay, and further on, you can vary the speed via the PWM settings over that speed pin. Okay, however, the generated motor speed is normally not a linear function of the PWM ratio signal, as we saw with the motor graphs that we saw earlier. So what we have to do is we have to do motor calibration, and that's done by measuring the motor at various speed settings between a 0 duty cycle and a 100% duty cycle, then entering the correct PW ratio in to achieve the desired actual motor speed in the calibration table. Motor calibration is important for robots that have differential drives, because remember, if it's going forward, both wheels would need to turn at the same rate. So if one turns slightly faster than the other, your robot would skew off either to the left or to the right, depending on which motor was spinning the most. Obviously, if it's turning on the spot or spinning on the spot, then one wheel would turn forward and one wheel would turn backwards, and one wheel would turn and one wheel would stop. So it would throw off your calculations. Okay, so this is why calibration is so important when you're using PWM. One other issue that we need to consider is direction control, because PWM lets us control the speed. So now, how do we control the direction? So it's possible to use two power supplies, like in a push-pull circuit shown previously, in this configuration. So there's your positive supply, there's your negative supply, and there's your ground. You've got your PWM signal coming in through one input and your direction signal coming in through another. So we can use this configuration using two AND gates and an inverter connected to the transistors. So in one situation, this transistor will be on, this transistor will be off, and you'll get a positive to ground path like so. So that will allow the motor to spin in one direction. Okay. Then in the other situation, when this one's turned off and this one is turned on, then obviously current flows from a high potential to a low potential, so there's your negative supply, there's your ground, so you'd get the current going like that. So you would get the motor spinning in the opposite direction, so that gives you your directional control. Modern switching electronics also make it economical to use little more electronics in the power stage than to buy two power supplies. Okay, so instead of having to buy two expensive power supplies, which will obviously weigh your robot down, the appropriate system would be to use a H-bridge configuration or Wheatstone bridge configuration. When you've got diagonal transistors which are switched correctly, then the current is directed through the motor according to a literal directional logic and the PWM signal, and then you can buy them on the pack on integrated circuit packages such as the L298N, which are quite nice little effective systems. Okay, the disadvantages of PWM are the current control is more difficult. Sometimes if you have fast switching of large currents, you get electrical noise and electromagnetic compatibility issues. That's what EMC stands for. And when a repetition frequency is chosen too low, it can be audible, which can be annoying to the people around it as well. Okay, so these are some of the implications when you're using PWM, which aren't exactly the ones you want. Okay, so this is the circuit of the H-bridge, and for most applications we want to be able to do two things with the motor. We want to run it forwards and backwards, and we want to modify its speed. So a H-bridge is what is needed to enable this motor to run forwards and backwards. Okay, Obviously, as you can see from the circuit, it's set up in a letter H configuration. Okay, so we have the motor with two terminals A and B, so A there and B there, and a power supply with a positive and a negative on it, and we're closing switches 1 and 2 uh, at the same time, and the motor runs in one direction, so that's this situation that we've got here. So the current would go through the motor like that and cause the motor, in this instance in the figure, to spin in a clockwise direction. Okay, closing circuits 3 and 4 in the same way would give you this situation here, which would then allow the current to move through the DC motor in the opposite direction as such, and that would cause the motor in this instance to rotate in a counterclockwise direction. So we effectively change the speed, and when we combine that with the PWM, we can change the speed as well. Okay. So the way to implement a H-bridge when using a microcontroller is to use a power amplifier chip in combination with the digital output pins of the controller or add an additional latch. This is required because the digital outputs from a microcontroller have very severe output power restrictions. They can only be used to drive other logic chips and never a motor directly. So since a motor can draw a lot of power, for example over 1 amp or more, connecting this to the digital outputs directly to a motor can actually destroy and blow up your microcontroller. Okay. A typical power amplifier chip containing two separate amplifiers would be an L293D from SGS Thomson. Okay, and basically you can connect an XY direction into a power amplifier chip, so you have an X, Y, and a speed that you can then connect to the motor configuration. Okay, and if you want, we can go through more about that in one of the tutorial sessions if you want to. When you're using the power amplifier chip, since the positive and negative inputs which will be connected to it, like the XY pins respectively, since these are electrically decoupled from the motor, they can be directly linked to the outputs of the microcontroller. So the direction of the motor can be specified by the software, for example by setting an output X to logic 1 and an output Y to logic 0. And since X and Y are always the opposite of each other, they can be substituted by a single output port and a negator, and then the rotation speed can be determined by the speed input, which would be linked to the pulse width modulation output. Okay, and there are two possible ways of stopping the motor. You either set both X and Y to logic 0 or both to logic 1, or you simply set the speed to 0. So it gives you a lot of additional control when using a H-bridge, and this is why we use them so much in robotics. The problems, however, are that if the transistors are driven into the on state, then the saturation voltage across them is relatively small, and as a result, the voltage applied to the base of the transistor must be higher than the supply voltage, which isn't possible. And these are particularly pronounced with power FET devices, such as the International Rectifier 8200. So you might need a bootstrap circuit in order to compensate for that problem. So like I said, I've mentioned all this about the power amplifiers. So you have your two outputs and it's decoupled from the motor. So there's your circuit, so there's your X, there's your Y, there's your speed. So this is what I was talking about when I was on the H-bridge slide a few slides ago. Okay, so I'll move on now to talk about servos. So DC motors are sometimes referred to as servo motors. This is not what is meant by the term servo, however. A servo motor, such as the one shown here on the right, is a high quality DC motor that quantifies to be used in a servoing application. That is meant that it has some form of closed loop control associated with it. Such as it's a motor that must be able to handle fast changes in position, speed and acceleration, and must be rated for high intermittent torque. So you can use these to build things like robot arms, for example. And I've supervised projects in the past where students have actually built their own robot arm using servo motors such as this. Okay, so a servo is a DC motor with the encapsulated pulse modulation control, and it's mainly used for building robotic manipulation. You can mount cameras on them, so you can do stereo vision systems with them, and they're really good. Servo has 3 wires, so it has a VCC, which is this red wire here. It's got obviously a ground, which is black wire, and it's got a PWM control signal, which is usually the white wire. So unlike PWM for DC motors, the input signal for servos is not transformed into velocity. Okay. So as I said, it's not transformed into velocity. It's instead used as an analog control input to specify the desired position of the rotating head. So if you wanted it to turn around, look around, you would alter the PWM and it would look in different positions. Okay, so it can't rotate continuously like a DC motor. Most of them only have a range from about plus or minus 120 degrees from its initial middle position. That's the main thing, its initial middle position. Okay, and it initially internally servo combines a DC motor with a simple feedback circuit, often using a potentiometer to sense the servo head's recent position. Okay. For example, a PW signal used for servos always has a frequency of 50 Hz, so pulses are generated every 20 milliseconds, and the width of each pulse specifies the desired position of the servo's disk, such as this shown here. So, with a certain PWM cycle, such as this shown here, it would look over here. With this width here, it would be in its neutral position, and if it's slightly wider, it would look into this position. Okay, so it's quite good. So for example, if you had a width of 0.7 milliseconds, that would cause the disk to rotate to its most position. So like this one of 120 minus 120 degrees. If it had a width of 1.7 milliseconds, it would rotate to its rightmost position, such as this. Each specification pulse duration is on the datasheet associated with each type of servo, so please be aware of that. Okay. Like stepper motor, which we'll cover in a second, servos are very simple for and good for simple solutions in robotics. However, servos also have a drawback, same as stepper motors do, is they don't provide any feedback to the outside. So when you're applying a certain pulse signal to a servo, you don't actually know that it's reached its desired position or not. Okay, for example, if it's got a load that's too high, or if there's something in its way. So you need to come up with ways to compensate for that when you're designing your system. Okay. Okay, so the last aspect that we'll cover today is on stepper motors. Okay, and stepper motors are used in many different situations where it's advantageous to control the robot in open loop mode, and feedback is not necessary or desirable. Okay, so from a control point of view, the motor regards a black box. You send pulses into it, and the pulses are counted on the microcontroller to represent the motion. You can then combine all those pulses together to represent the distance of pulses and make that proportional to speed. By knowing this information, you can know how far you actually travelled. So if you know your wheel circumference, then you can calculate how much one step would equate to distance, and assuming there's no wheel slippage, you can then calculate where you are, and that's a process called dead reckoning. Okay, it's how ancient ships used to navigate. Okay, by knowing what direction you're going on, how fast you're going, you can approximate where you are and when you're going to get to your destination. Okay, we'll cover more about that in future lectures. So here you've obviously got an energized coil, you've got a stator, you've got a rotor, you've got your stator core here, and these dotted lines here represent your magnetic path. So stepper motors differ from DC motors in such a way that they have 2 or more independent coils which are independently controlled. Okay, as a result, the stepper motor can be moved by sending pulses into these coils to exact a single step forwards or backwards instead of a smooth continuous motion. For example, a typical number of steps per revolution could be about 200, resulting in a step size of about 1.8. So if you do half stepping, that would give you a half step size of 0.9, which means you end up with an extremely accurate and precise method of controlling your motor and where it is. Okay. Some stepper motors allow half steps, and some even result in a finer micro stepping process where you can vary the voltage on each coil, which allow you to go to actual fractions of a degree. And they're extremely useful for things like in astrophysics, where you want to make the parabolic mirror of a telescope fitting for your application, because you can't make them out of big pieces of glass anymore because they warp. So stepper motors, mounting bits of glass on stepper motors, allow you to change parabolic mirror curves, and that's one application of what you can do with servos or stepper motors. Okay. There can also be a maximum number of steps that you can do per second depending upon the load and the specifications of the actual motor. Okay. So you could imagine that you have a stepper motor which has two coils in it, an A and an A dash, and a B and a B dash. So the two coils are indicated by two H bridges, for example. Each has a four cycle advances by the motor by a single step if executed in the order. So by executing the steps in like a binary sequence, so step 1 would be 1 1, step 2 would be 0 1, step 3 would be 0 0, step 4 would be 0 1, then you can go through all the different combinations. And stepper motors seem to be a simple choice for building robots because, considering the effort for velocity control, positional control, they're very good to do, but it's just related to the number of pulses that you can use. However, stepper motors are very rarely used for driving mobile robots in real applications because of the lack of feedback on the load and the actual speed. So, for example, determining if you've got missed steps or if you've got wheel slippage. So, it's in addition to requiring double the power electronics, stepper motors also have a worse weight to performance ratio than DC motors, which is again why they're not used in big industrial robots such as ABB. Okay, so while they're good, they do have their drawbacks and their limitations. Okay, but hopefully that's given you a bit of an insight into stepper. That's just some more information on hybrid stepper motors. There's also some more information on Moodle that you can look at about stepper motors as well. So full, half, and micro stepping. Okay, we mentioned these earlier on. I'm just going to give you a brief overview of what they are. So single stepping. So imagine you've got the numbers on a clock. Okay, so single stepping would be if you start at 12, single step would take you to 3 o'clock, another single step would take you to 6 o'clock, another single step would take you to 9 o'clock, and then the next step would take you back to 12, and then you completed one set on energizing all the coils in one go. If it was half stepping, you start at 12, but instead of going to 3, you go to 1:30, you then go to 3 o'clock, 4:30, 6 o'clock, 7:30, 9 o'clock, 10:30, 11, and then you've completed one complete cycle. Okay, so you double the number of steps that you need per revolution, and it gives you a more accurate way of driving motors. Microstepping is, as I said before, is where you vary the voltage on each coil, and you can then go to fractions of a degree by making the rotor go between the coils. Okay, so it's a really useful way if you want really fast precision, and we can go over some of that in the tutorial if you want me to elaborate on that further. Okay, so that comes to the end of this lecture. So there's some topics for further reading. So you can talk about constant current, constant voltage, chopper drives, and practical pull-out torque methods for driving stepper motors. And there's some, like I said earlier, there's some stepper motor control examples on Moodle and some extra papers that we can go through in the tutorial sessions. So I hope you found that interesting, useful, and I'll look forward to seeing you again for lecture number 3 when we'll start talking about robotic perception. Have a good night, and I'll see you soon. Thank you very much.